Hi there, thanks for joining this video on the Technisci channel. This is video 3 in the beam series and we are doing overhanging beams. Now overhanging beams are those that have both ends overhanging the reactions, or you will see some with only one end overhanging the reaction, also being called overhanging beams. So in this video we are doing our shear force diagram. We're going to be determining or calculating our reactions as well as our max bending moment. And bonus, I am using a beam that has a uniformly distributed load. So you're getting the opportunity to see how to treat these questions so that you can determine the reactions with ease. Are you ready? Let's go. Grab your computer, your T-square, set square, pencil, whatever you need to get you through this video. Stick with me right to the end so that you can master this concept. Let's go. Now here we have the overhanging beam that we're going to be working with for this video. Notice it has two loads on it, but I want you to pay keen attention because it has a uniformly distributed load. And if you watched video 1 in this series, you would have seen where I gave an example of how you could identify a UDL. This right here tells you it's a UDL. It says 30 kilonewtons per meter. The slash means per. Now for this example, we're seeing where the UDL can be interpreted to be the weight of the beam, especially given how it is written and the fact that it spans the full length of the beam. But that's not necessarily the case. And what I'm going to be doing, I'm going to be using the method where I convert the UDL into a single point load. So I'm going to go now and show how we go about converting from this UDL to a point load. So let me just move to the side. And now we are going to start drawing so that we can have our free body diagram to represent what is in this question. So we have a distance of 1.2, 3.6, and 1.0. Remember, on our space diagram, which is what is our free body diagram, we represent the spaces to a suitable scale. Now, given that this is 1.2, 3.6, and 1.0, I'm going to be using a scale of 10 millimeters to represent 1 meter. So that would simply mean that this 1.2 meters would be 12, and this 3.6, all I'm doing basically is just multiplying all the values by 10. So this 3.6 would be 36, and that 1.0 would be 10. Then I'm going to be putting on my arrows. So I'm just going to put in my reactions now. So one should be there and one is here. And again, like I say, what I do is I draw each segment of my beam so that it's easy for me to locate where the loads or the reactions are. So this diagram is now representing my beam and the loads that are applied. However, it is yet to have the uniformly distributed load represented. So let's go about calculating so that we can decide how much this load is in total and position it at the center of the beam. So to do that, I'm going to get my calculator. So it's 30 kilonewtons per meter. So what I'm going to do is just to add all the distances that are here. So the total distance of the beam is 5.8 meters. And if every meter of this beam has 30 newtons, then I'm going to now multiply this distance by 30 to determine the total load acting on the beam. And we get 174, and that would be kilonewtons. So now I'm going to be copying this arrow and I'm going to be putting it in the middle. Now, because of how these loads are, I can't just go and say this is the middle of the beam because it really isn't. It's the middle of this aspect. So what I'm going to do is to use M2P, which is the mid between 2 points, to locate the exact position. And that's where it placed it. So notice, though it is close to where the center point was, it is not quite. And that is why it is very important that you ensure that you place the arrow representing that UDL in the middle. So use M2P, then click the two ends of the beam for this arrow now to end up in the middle. So now I'm going to be labeling the loads and the reactions so that our beam can be properly represented. And I'm just going to copy to save time. So now my beam is fully represented in terms of the loads and the reactions. So we have the two given, 10 and 20 on each end, both reactions, and we converted the uniformly distributed load to a point load, and that had a value of 174 kilonewtons. So now I'm going to go and label the spaces according to Bose notation. So just a guide when you are labeling your spaces, always try to get the first load acting on the beam from left to be AB. Okay, so now I'm just going to represent the scale that we're using, and then we can get to doing our load line. So there we have our space diagram scale. And as you're seeing 10 to 1, which is what we used, you know that this is a scale of magnification. So this diagram is actually larger than the units at a factor of 10 times bigger. So now we are ready to go to our load line. And just a little side note in terms of showing how you got your UDL to be converted to a point load of this magnitude, you can simply put that as a little note in your diagram, in your solution. So UDL to point load. You can always create a little formula. So UDL to point load would be equal to, so that's 30 kilonewtons per meter times 5.8 meters, and that's equal to 174 kilonewtons. So we can add that as a little note as part of our solution. So now I'm going to go to what's next. We've done our space diagram, added our space diagram scale. Yes, we're going to our load line. Now, given our loads are 10, 174, and 20, the most suited scale would be one that is 1 to 10. So I'm going to use 1 millimeter to represent load of 10 kilonewtons. So now I'm going to be dividing each value by 10. So that is 10 divided by 10, 1. 174 divided by 10 is 17.4. And 20 divided by 10 is 2. So you can see that the uniformly distributed load is a very large load. So now we're going to put in our points. I'm going to put a distance of 10. So now I'm going to be connecting each end of my load line to the point. I now have my polar polygon, so I'm going to be labeling and putting in the scale. So good. So we now have our load line and polar polygon represented, and each load is represented. So AB is represented, and this member is AB. Then we have BC, BC being this member here. CD is this. And so all the loads that are being applied on the beam are represented. So now we're going to go through to get our link polygon and then to determine our reactions, which was the first thing that was on our list of things to do. So now we're going to put in our hidden lines. So I hope you would have caught the first two videos on beams, and so you are able to quickly move along with me to complete this diagram. So again, I'm going to do the color coding. So again, remember, each member from the polar polygon should be copied and fit within the space that represents that letter. So I have here AO, and it's going to fit within the space that represents A. And remember, let me just shift this a little. A is represented between these two loads. And now B, following the same pattern, B likewise starts from this point and stretches over to this line. So again, B2 has to go there. And I'm going to extend it to where it goes. And B goes over to that point. Next, we're taking C. So once you follow the principle, each line from the polar polygon is covering the space. Once you do that, you cannot go wrong. I don't think this blue is showing so well, so let me change the color. So C went all the way over here. So now we're going to look at D. And D is spanning the distance between these two loads. So D comes here. Let me just make sure it covers that span. Yes, it does. So that is my link polygon now, but it is not closed, so I'm just going to be drawing in the closing side. And I'm going to be coloring it. So now, as you know, this line now goes over to our polar polygon. And this now represents width space. Width space is that closing side representing. You can look at your link polygon to see which space it spans. And that, of course, is the space between the two reactions, and that is space E. I'm just going to do some labeling for my link polygon, and then we'll be right back. You can also opt to put arrows on your link polygon. That is a choice that you can make. Okay, so now that we're done that, we can go and look at what was required of us for this question. We need to find the reactions. And as I said last time, at this point, we can go ahead and find our reactions. Okay, so there we have it, but this is not quite the complete answer, because here 1 millimeter is representing 10 kilonewtons. And another way we could remember that this is not quite the set value, remember that the sum of those going down should be equal to the sum of those going up. And already we can see that this is far in excess of 100. So the sum of the reactions couldn't be less than 100. So we know we need to convert these according to the scale we're using. So our right reaction by Bose notation would be called dE. So this is the value that represents dE, that's 10.4. So that's 10.4 millimeters, which is now going to be equal to that value times 10, 104, and it's kilonewtons when we convert it to scale. So again, 1 millimeter representing 10 kilonewtons. So whatever value we measure and get, we must multiply that by 10 to get the kilonewton equivalent. And this is dE. And our next reaction by Bose notation is EA. And so the dimension from E to A will represent its magnitude. And this is 10. So again, it's 10 millimeters, which would be equal to, that times 10, 100 kilonewtons. So we could actually do a test to see if the sum we're getting for the upward, which are the reactions, is in fact equal to the sum of the downward. 204, good. And the sum here is also equal to 204. So we have met one of the conditions for equilibrium. So we can almost kind of rest assured that our answer is correct. As long as the sum of our reactions is equal to the sum of the downward forces, then we are more or less correct. Very good job. So now we have done the first item or the first criteria. We're now going to be drawing our shear force diagram. And I'm going to turn on my line weight for this one. Now, if you recall what I would have said in the last video, and again, if you have not watched those videos as yet, it is critical that you do, because those videos will be helping you to understand all of the concepts a little better than we are here, because we would have done it twice already. So we're really and truly just going through as reinforcing through repetition. So we're really just reinforcing. So I'm not spending as much time to go into the nitty-gritty of what I'm doing as I would have done in the first two videos. So if you missed those videos, I'll link it in the iCard and put it in the description. So let's go now for our shear force diagram. So again, we are going to be representing space and on the corresponding line from our load line. All right, so we're now going to put our horizontal line on A and on A from the load line. Now, this can be a little bit tricky, but do not be confused. X covers this span, as we know, but guess what? B now covers this span from here over to here. So that is B. At A, it went down to B, so I'm going to go down. All right? So at B now here, we encounter a load. So we go down, then we go all the way across to C. At C, we encounter a load going down, and it goes down. We're now at space D. Space D covers this span. At that point, we go up, and we're going up to where? E. We haven't put that in yet. So again, as I said, I don't normally put that in just to avoid confusion. So I've put it now, and we can continue. So from D here, we go up and we go to E. Then we go across into space E. And then at E, we go up to A. And there you recognize that though you may have been a little bit confused as to what to do with A, you realize that our diagram ended up closing. And so we now can see our shear force diagram for our overhanging beam. Notice it's looking mightily different from our other diagrams, but this is typically what your shear force diagram will look like for an overhanging beam. So I'll just again go and finish labeling. So remember, when labeling, pay attention to which line each aspect of the shear force diagram is on, and top that as well as the space within which. So you ensure that you have labeled it correctly. So we've now done the first and second criteria for this question. We are now on to the final one, which is to determine the max bending moment. Do you remember how we did that? Okay, well, let's go right into it and see if you remembered indeed. So the first thing I'll ask is, how do we determine where we have max bending moment or where shear force is 0? Now, this can be a little bit difficult if you do not remember precisely what I said, because you have a vertical member intersecting horizontal here, one here, one here. How do you tell which one will be the point along which shear force will be 0? Good. If you said the point between both reactions, then you would be absolutely correct. So this is the point at which, and I'm going to just put a point there. This is the point at which shear force is 0. So this is our point. It's along this line from our shear force diagram that the max bending moment will occur from our link or funicular or bending moment diagram. So we've now identified that, and I'm just going to be dimensioning that section of my link polygon. I'm going to just adjust the dimensions to see if it has any decimal at all. Okay, so we can leave it rounded there. Now, of course, for greater accuracy, you could use 14.03. That will definitely increase the accuracy with which you are measuring. Okay, so remember, this is the formula to calculate the max bending moment. But do you remember what A, B, C, and D stand for? Okay, so let's go. A is the value of the scale from the space diagram when you write your scale with 1 millimeter or in 1 millimeter. So now our scale is 10 millimeters to 1 meter. How do we get that 10 to a 1? We simply divide it by 10. And so whatever we do to one side, we must do to the other. So that would be 1 divided by 10 to give you 0.1. So now A would be this 0.1. So now B is our load line scale, and it is the value here when this is written to 1 millimeter. So we already have that, that's 10. C is our pole distance. Let's measure that. And our pole distance is 10. And then finally, D would be the height of the section along which you have max bending moment. So we have all our values now, and we just need to plug them in and do our calculations. So A was 0.1 times B was 10 times C is 10 times D is 14. And that would represent the max bending moment of this beam. So the max bending moment of this beam would be 140 kilonewton meters. And that basically wraps up this question, and we have done all 3 sections. Yay, we made it to the end, which means you would have stuck with me right through following the procedures that I would have shown. I hope you were working along with me. But remember, if you miss anything, you can just pause, go back, watch it again so that you are mastering this concept. Let me know in the chat how this is for you. And I just want to send a major big up to all the persons who've been sharing, liking, and giving me, the thumbs up to say keep going. I really appreciate it. And I really do hope that these videos are helping. You're making the concept much simpler so that you can understand and go and ace those exams. So catch me in the next one. See you until then.